4.3, connecting f prime and f double prime with the graph of f, part 1. Your objectives for this lesson are to apply the first derivative test for local extrema and to use derivatives to describe the graph of a function. Let's start off with the first derivative test for local extrema. So this applies for continuous functions, so a continuous function f of x. And you see that at a critical point C, if f prime changes sign from positive to negative, so positive to negative, at C, meaning that f prime was greater than 0 when x was less than c, and now after c, to the right of c, f prime is less than 0, then f, the original function, has a local maximum value at c. So you can see here in this graph, your derivative would be defined here because you have a nice smooth curve. Your f prime on this part is greater than 0, slope is slope is positive, and f prime is less than 0 on the right half, so your slope is negative. Here you have again f prime greater than 0, then f prime less than 0, but this would be a function for which f prime of c would not be defined because you see that point. Okay. Second up, at point C, if f prime changes sign from negative to positive at C, so f prime was negative to the left and now f prime is positive to the right, then f has a local min at C. So again, you see you have your negative slope, f prime is less than 0, then your positive slope, f prime is greater than 0, and here is point C. This function would be differentiable at C. Same thing here, except we have a corner at C, so your function is not differentiable at point C. Last up, if f prime does not change sign at C, so you either have f prime is negative and negative, or f prime is positive, positive, then f has no local extreme value at C. So in this case, you see this function continues to rise, and at C, it's not dipping down at all. It just continues to rise. F prime is positive on both sides. There's no max or min here. This case here, again, not differentiable at C, but you see that the derivative is negative to either side of C. Okay. At a left endpoint A, so this is talking about just one side, not at a point. Okay. If f prime is less than 0 for all x greater than a, then f has a local maximum at a. So that is this case here. I'm at the endpoint A, and I see f prime is less than 0 for all the values to the right. That means that A is a maximum. Now this second case here, what's in parentheses goes with what's in parentheses. So I'd say if f prime is greater than 0 for all values to the right of A, so greater than A, then we have a local minimum at A. Makes sense. Okay. At a right endpoint, B, so this is going to be basically the opposite of before. So if f prime is less than 0 or is negative for all the values less than my endpoint, so to the left of that endpoint, then I have a local minimum. So if it's falling off this side, everything's decreasing, this is a min. if everything is increasing up to b, so f prime is greater than 0 for everything less than b or to the left of b on the graph, then I have a local maximum at b. Some notes about this. Critical points of a function f partition the x-axis into intervals on which f prime is either positive or negative. We've been over that a little bit. To determine the sign of f prime in each interval, we're going to evaluate f prime for one value of x in the interval. Just one value. Then we'll apply the first derivative test for local extrema. Example 1. Find the critical points of f of x equals x cubed minus 12x minus 5. Find the function's local and absolute extreme values. Identify the intervals on which f is increasing or decreasing. The first thing that I want to do here is quickly just look at the graph of this function. Then we're going to solve this analytically, but let's look at the graph first. So when I graph this, y equals x cubed minus 12x minus 5. Let me zoom out just a little bit. Okay, so it's looking to me like I'm going to have two critical points. One's going to be a max over here and a min down here. But again, let's look at this analytically. So analytically, I know that this function is a continuous function because it's a polynomial function. All polynomials are continuous functions. So I know that I can find my derivative, which will be 3x squared minus 12. And the zeros of this function are the only critical points. There's nowhere that doesn't exist. So I'm just going to set this equal to 0. And I'm going to solve for x. So I've added 12, divide by 3, and I get x is plus or minus 2. So these are my critical points. X is plus or minus 2. And this is dividing my graph into intervals. So I'm going to make a sign chart. Let me actually move this over. So the first part of this up here, I'm going to label intervals. And this is the sign of f prime and behavior of f. Okay, my first interval is from negative infinity to negative 2. Between negative infinity and negative 2. Stops right at this first critical point. The next interval will be negative 2 to positive 2. And last will be at 2 to positive infinity. What is the sign of f prime in my first interval? Well, let's find out. I know that f prime is 3x minus 12. If I plug in a negative 3 that's in this interval, I have 3, x is negative 3, oh, not squared, 3x minus 12. Oh, it was squared. Okay. So I get negative 3 squared is 9 times 3 is 27 minus 12. I get 15. So this is a positive number. On this interval, I'm going to choose 0 to plug in because 0's in there. It's a nice, easy one to plug in. So I get, well, this cancels. And I'm left with negative 12. So my sign is negative. On this interval, I'm going to choose 3. And I get the same answer that I got before since 3 squared is 9. Just like negative 3 squared is 9. So I'm going to have a 15 here. So that's a positive number. So I have plus, minus, plus, which means that here my graph is increasing or rising. Here f is decreasing or falling. And last, we are increasing again. Okay, so that means I'm going up, down, up. What did I want to ask here? Okay, so we need to find our local and absolute extreme values. For this function, since it is cubic, there is not going to be an absolute max or min. It's going to keep going on to infinity. But we do have a local max at x is negative 2 and a local min at x is 2. Let's find out what those are. So we want to know f of negative 2 is negative 2 cubed minus 12 times negative 2 minus 5. So this is negative 8 plus 24 minus 5. Negative 8 and negative 5 is negative 13, so this is 11. And f of 2 is 2 cubed minus 12 times 2 minus 5. So this is 8 minus 24 minus 5. So that's a negative 29, negative 21. Okay. So this means I have a local max at negative 211, a local min at 2 comma negative 21. I said no absolute extrema, increases on the interval negative infinity to negative 2 and 2 to infinity, and it decreases on the interval negative 2 comma 2. Okay, so this whole big chunk is our answer. A little bit of work, but really not too bad. Example 2. Find the critical points of f of x equals, parentheses, x squared minus 3, close parentheses, times e to the x. Find the function's local and absolute extreme values, and identify the intervals on which f is increasing and decreasing. Okay, so just like before, I'm going to recognize that this polynomial is a continuous function, e to the x is a continuous function. The whole thing is continuous. And I don't have any division by variables, so basically the only place where I'm going to have critical points is where the derivative, f prime, equals 0. So let's find f prime. And I do have to use the product rule here. This part is u times b. So I have u Oh gosh, why did I write a U there? Times the derivative of e to the x is e to the x, plus derivative of this function is 2x times e to the x. Okay, so this is my derivative. And I'm going to set it equal to 0. What I'm going to do now is factor out an e to the x because each of these terms has one. And divide by e to the x. Before you worry that I'm getting rid of a valuable x here, remember that e to the x will never be equal to 0. So because e is a positive number, it's never going to be equal to 0. Okay, so now we just have a nice quadratic here, which I can rewrite x squared plus 2x minus 3. And this is fairly easy to factor. So I have x plus 3 and x minus 1. So I get x plus 3 equals 0 or x minus 1 equals 0. Which leaves me with x is negative 3 or x is 1. Okay, so these are my 2 critical points. That's all that work got me was my critical points. And now that I have them, I'm going to make my sign chart. Okay. So this is the sign of f prime and behavior of f. My first interval, since this was a continuous function, no endpoints, is going to be negative infinity to negative 3. Then we have negative 3 to 1. And last up, 1 comma infinity. Okay. Here we go. Plugging in to f prime to figure out our sign. I'm going to do a negative 4 first. So when x is negative 4, then I'm going to do a 0 for there, and I'll do 2 over here. Okay, so my derivative. And why don't I actually just use this piece here that's a little bit simpler. So e to the x times x squared plus 2x minus 3. Okay, so e to the 4 times 4 squared plus 2 times 4 minus 3. Okay, so I know this will be positive. Let's see what the inside will be, because we're really just after the sign. So this is 16 plus 8 minus 3, which gives me 21. So this is going to be positive. Okay, moving on to x equals 0. So I'm going to plug in a 0 in for all my x's. I have e to the 0 times 0 squared plus 2 times 0 minus 3. So those zeros go away. This e to the 0 is a 1 times negative 3. That's a negative 3. So negative, and okay, x equals 2. We have e squared times 2 squared plus 2 times 2 minus 3. So e squared is positive times 4 plus 4 minus 3. This is a 5, so I get 5e squared, which is positive. Okay. So that means we're rising, falling, rising, increasing, decreasing, increasing. Which means I have a max at -3 and a min at 1. Okay, so let's write our conclusion and be done with this first part of the lesson. I have a local max. I said that was at x equals -3, so it'll be -3, comma, what happens when I plug into my original function. So -3 squared minus 3 times e to the -3. I get this is 9 minus 3, so 6 e to the -3 is approximately 0.299. And then, so 0.299, so I have a local min at 1, comma, let's see. So if I plug in a 1, I'm going to get 1 squared minus 3 times e to the 1. So I get -2e, which is approximately equal to -5.437. Okay. And I also want absolute mins and maxes. Well, you peek a look at the graph of this local min is also the absolute min, and there is no absolute max. Okay. The function is increasing on -infinity, comma -3, and 1, comma infinity. And it decreases on -3, comma 1. So that is your answer.